So far in our class, we've studied a lot of abstract concepts such as limits, derivatives, and all of the rules that come with doing such. And examining with, say, exponentials and logs, how those rules affect those types of functions as well. In chapter 3, we kind of divert from the abstract and focus on actually applying calculus, such as limits and derivatives, to actually determine the traits of a mathematical curve or function. And obviously, we're going to be focusing on how we can use this in the business world as well as in other subjects. But, the thing I wanted to start off with the first section is talking about graphical traits of functions, such as intervals of increasing, decreasing, minimums, maximums, and other terms like that. And then we'll talk about how can we use calculus to actually determine those things. So, for example, if we imagine the life cycle of a particular product that is being sold, there's often a lot of change that's associated with that. When a product is introduced, it often goes through rapid growth at the beginning, where sales increase very, very quickly due to the nature of word of mouth and spread. Where at some point it hits like a limiting value, where it's hitting the maximum amount that the customers will want to buy, which is often called the maturity window of that. And then often after hitting maturity, it will decrease over time as more and more people have the product, less people want to buy it. And sometimes it will go through a decline, and even at certain points could go through a rejuvenation period later on and kind of go up and down and up and down. Relatively common. So now, not all types of products follow exactly this graph, but you can use your imagination how we'd often want to study these sorts of trends if we were predicting our supply, demand, our sales, and such. But basically, one of the ideas brought about by this graph is how can we use calculus to analyze these sorts of things? And one trait of a function or a graph or whatever you want to call it is the pattern of getting growing or decaying, getting larger, getting smaller, or increasing and decreasing is another way to put it. And that's kind of the first thing we want to discuss. Before we talk about how you can determine it in calculus, basically I wanted to define how do we write our answers. If I ask you to determine what are the intervals of increasing and decreasing, like looking at a graph, we can first of all, increasing and decreasing is always done from left to right. So looking at this graph, it's sort of like if the x-axis is our time period, we're always imagining time is moving forward. And so in this example of a product lifestyle, the sales are increasing up until a certain point where they begin decreasing and increasing, and every sort of function could have these ebbs and flows, ups and downs. And so anyways, there's the more formal way of defining it, mathematically speaking, is that if a function is increasing, every value of f of b would be larger than the value at f of a. So one way it's written is for all values of b larger than a, f of b must also be larger than a, implying that as we're moving to the right, the y value f of b is always increasing as x increases. Now, if it's decreasing as x increases, y will be decreasing instead. So again, that could be written, a lot of times it's written in a formalized definition as if b is greater than a, then g of b is less than g of a, meaning it's getting smaller as time progresses. But another thing I wanted you to notice about functions which are increasing or decreasing is if we looked at the secant line, say for example we connected these 2 points on a decreasing curve, notice that the slope in between those 2 points is positive, right? If we were to do the rise of a run, it would be f of the average rate of change, or however you want to call it. It would be increasing because it's going up and to the right, as we know about slope. And when it's decreasing, the secant lines connecting those points would be decreasing instead. And this is the essence of how we use calculus to determine if a curve is increasing or decreasing. It has to do with the slope and whether it is positive slope or negative slope. Negative slope indicates decreasing, positive indicates increasing. And the reason we can't use average rate of change to determine this is because it's averaged. Like say for example on the product life cycle, if we chose these 2 points as the points for our secant line, we could see that would give us a negative slope, and that would be decreasing. But it's not, as we talked about before, the average rate of change is not perfect, because say for example I took these 2 points and I got a secant line like that. What does that indicate? Because if we're taking a particular width interval, it might not necessarily reflect the proper slope of the curve. And that's why a derivative is better, because a tangent line gives us the slope at a particular point, and that will tell us whether it's increasing or decreasing. So kind of spoiling, the next video is going to be more about that, but basically positive slope means increasing, so therefore positive derivative means increasing, because that's what the derivative function does, gives us the slope of the curve at every point in time. But before we get to that, let's talk about how we actually write intervals of increasing and decreasing. So let's look at an example. It says the following, below is the function which gives a person's weight at age X in years. So basically here we have a graph which is describing the weight in pounds of somebody as they get older. And it looks like, from, when they're born, well, it appears as though they weigh 0 pounds, which is probably not very accurate, but we can use our imagination and say, okay, this is probably not 0. But, they're getting larger and larger and larger up until they reach, it appears to be about 25, where they hit a point where they level off and they're look to be a consistent weight of 150. Then when they hit 35, they gain a bunch of weight. Very, very common for people to gain weight in their 30s or 40s. And then at some point they realize, okay, I'm heavier than I want to be, and they lose weight and whatever. And they appear to be roughly 160 pounds until 80 years, which who knows, do they die? I don't know. The graph doesn't tell us, not to be morbid, but using the information we have there, we have it. But basically we can see, it's increasing for this first interval, and how we write it mathematically speaking is, if you're ever asked to determine an interval in which the function is increasing, you use the domain, you do not use the range. And I'll try to explain why this is the case, but basically what you can imagine is connecting it down to the x-axis. For some reason my pen's not working once again, but if you connect this down to the x-axis, it's increasing on this interval, that part of the domain, from 0 to 25. And basically we're just going to use interval notation to do this, which is just, from 0 to 25. And a question I've been asked before is, should I use brackets or parentheses for intervals of increasing and decreasing? And what I like to say is you can use either. It really depends on the textbook and the source in terms of how they define increasing and decreasing, because I've seen it defined both ways. Because another thing you might say is, well, when they're exactly age 25, are they exactly getting larger or are they flat? Which is it? To which you could say, well, both or neither. But at the end of the day, it doesn't really matter to me if you use parentheses or brackets. I'm just in the habit of using brackets. But be wary of every textbook's a little different. Anyways, it's not super important. And on an exam, I wouldn't care either way. Okay, and then and also we don't want to use the let's finish doing it this, and then I'll try to come back to why you don't want to use the range values for describing such intervals. And then from age 25 to 35, we'd say their weight was a constant, meaning it's not changing. So 25 to 35, their age was a constant. And again, this notation just means all values in between, basically. Also, this probably isn't very realistic. They're probably not exactly 150 pounds for 10 years. There probably is some fluctuation, but again, take the graph with a grain of salt. And then I can kind of look at the next interval. So then from age 35 to, it appears to be about 40, their age is their weight is increasing once again. And again, when we're writing intervals of numbers, we often use the union symbol. It looks kind of like a U. It's technically called the cup symbol, which just means that we're saying it's sort of like, or it could be their weight was increasing from ages 0 to 25, or it was increasing from age 35 to 40. And then from age 40 to 50, they were losing weight. So that's where we'd say their weight was decreasing in that interval. And then from ages 50 onwards, let's just say 50 to 80, their weight was constant. And anyways, again, this is how we describe it. Always use x values of your function to describe intervals of increasing and decreasing. And again, the reason why we don't want to use y values is because let's say I referred to this interval by the y values. Let's say I said, well, from 150 to 200. First of all, usually we describe these processes using the time frame, not the weight frame. Like if I was, wanted to know when my it's about my weight. When is my weight increasing? It's the x-axis. It's not about, you know, what years my weight was, or what weight my years was increasing by, if you see what I'm saying. But x is always our variable that kind of creates the behavior in y. So when we're asking ourselves, how is the graph changing? It's how y changes with respect to x, which is why we answer based on x. But if we were to answer it this way, this is not very specific because the weight was fluctuating between 150 and 200. Well, really, when it was decreasing, it was more like 160 to 200. But since the function doubles back on itself, there's a lot of different times where their weight was 150, and you can't answer this with just a singular answer. So it doesn't really make sense to do it that way anyways. So looking at another example, let's say we're examining this curve over here, and we want to know when this is increasing. Again, basically how I would do it is I would go left to right and just take every, trace my curve along the graph, and for each, in this case it's labeled with points, but for each point along the way, we would determine that interval. So also another word of caution here is, like, if you look at this particular part of this curve, a very common mistake here would be to say this is actually increasing, because if you look at it, it's going up. But notice, like I said before, increasing and decreasing is always done from left to right. If we go from left to right, it's decreasing. It's not right to left, because that's backwards. Again, we're kind of imagining this is the flow of time this way. And again, like a metaphor I like to use is, imagine this is your bank account. Starting from the left, this is your current value, and then this is describing the fluctuation. It's going down, even though the arrow is pointed upwards. That doesn't matter. It's not about the arrow, it's about left to right. So anyways, and looking, this appears to be 1, 2, 3, 4, 5 to the left. So from minus infinity to -5, this curve appears to be increasing. So we'll go ahead and write out, what are the intervals increasing, what are the intervals of decreasing, and then sorry, it's decreasing, as I said. Don't make that mistake. I just spent a good minute talking about why this is decreasing, not increasing. Then it's increasing from -5 to -3. Again, we're using our x values to describe these intervals. Then it's constant from -3 to -1. And it doesn't ask us to find those intervals of constants, which it usually will not. And it's actually very uncommon for a function to be constant unless it is a constant function. So most of the time we don't, this behavior is uncommon, which is why they don't ask you for this. But we'll just ignore that. And then from -1 to 1, it is increasing yet again. Then from 1 down to 4, again, using the x values on this interval, it's decreasing when x goes from 1 to 4. And then when x moves from 4 to 5, it's going back to increasing. And it appears to be constant from 5 to infinity. In the next video, we will talk about how we can use calculus to figure out these intervals in a similar way.